So this is 8.2, and it's called estimating a population. I don't know why I decided to not capitalize that. So we are going to create confidence intervals. About proportions. But before we do that, we have conditions, okay? So we have some conditions for constructing a confidence interval. If you are ever asked any question of some sort to construct a confidence interval for a proportion, and you do not check these conditions, you are wrong. So don't be wrong. Check the conditions. Right? Before you wreck those conditions. All right. First thing you got to check is that the data is random, that the data comes from an SRS. A simple random sample, right? Also, you got to check the 10% condition. When sampling without replacement. I'm not sure why you would ever sample with replacement, but it's in there, right? Why would you do an experiment on the same person twice? Unless it was a matched pairs experiment, right? Anyhow, number 2, right? And we know the 10% condition is that is this? I'll just write it down. Yeah, little n. And okay, number 2. Large counts. So we got to check that both these conditions, right? NP hat and n times 1 minus p hat are at least 10. Why is that important? Because you need to be able to use the standard deviation of your sample for your p-hat, right? In order to calculate a confidence interval. If this condition is not met, then you cannot use you cannot use that sigma sub p-hat, right? The standard deviation of your sample proportion. All right. Now that we know those things, we can go ahead and try some. All right. Wow, this needs to be a little larger. Get a couple of. That's it. Those are the 2 conditions that need to be met. That didn't work out for me. You violate your rules. Oh well. Alright, so Miss Quinn's class, they want to construct a confidence interval for the proportion of p pennies more than 10 years old in their collection. Apparently they have a penny collection in this class. It's way more than in my class. Because we don't have a penny collection. Sorry guys. We can work on it. We can work on it. I don't know what constitutes a good penny collection, but we can do some research. Right. So our sample had 57 pennies that were more than 10 years old, 45 pennies that were almost 10 years old. That's about easy. Okay. Let's check the conditions. All right. So what do we need to know? We need to know. Is it a random sample? Doesn't know what to say. Well, I guess we can assume it's a simple random sample. Okay. Assume an SRS of what size? 57 and 45. So 102. You gotta watch me today. I'm probably not gonna. I'm probably gonna make mistakes. Watch me. Like I might have had it wrong today. So, all right. Okay, 102. All right. Is it big enough? Can we assume that 102 is less than or equal to 1/10 of all pennies? I think that's definitely checked. Okay. Because there are a lot of pennies. We need to look at their collection. All right, let's actually do the math. All right, let's check out the condition for large counts. And I guess this is true, really, if the collection, going back, sorry, is larger than 1,020 pennies. It doesn't say that, but we can go ahead and assume that that's true and move on. Alright, so we're going to say, hey, we can do this if we assume that the collection is at least this large. So for large counts, let's check. Is So first of all, we need to know what p hat is, right? What is p hat? Our sample. Um, all right, so let's look at the proportion of pennies that are more than 10 years old. Because what are we interested in? The proportion of pennies that are more than 10 years old. Okay, cool. So more than 10 years old, we had 57 over 102. So p hat is 0 point, approximately 0.5. 6 if we round to the thousandth place. Right. 559. No, I mean you can. It's right. Yeah, you can, but this is a. I feel like it's an easier word number to work with. If you like working with the fractions, it's not wrong. Okay, so now we can check our condition that n times p hat is at least 10. Which is certainly going to check out, right? And then also that n times 1 minus p hat is greater than or equal to 10. And that's going to check as well, right? So there we go. We did it. We checked the conditions. Okay, so we're going to construct the confidence interval. And in order to do that, we use critical values. We talked about this a little bit, right? All right, there we go. This is crazy. All right, so we estimate at a level of confidence. So here's our normal curve. First thing we're going to have with a proportion is we're going to have, let's just call it, we know it's P anyways, but let's just call it so P in this case. We're going to have a margin of error this way or this way. That's going to be represented by our standard deviation, right? So over here, this interval is going to be the square root of p times 1 minus b. Oh, sorry, the square root of all that over n, right? And over here, we'll have the same interval. So we'll assume that this is 1 standard deviation away. Right, so now if we change that, what we're doing is we're looking at a sample proportion now, right? Because in most cases, that's what we're going to be dealing with. We're not going to be dealing with an actual proportion. Okay. what this is this is our standard error of p hat. Okay? But we also need a critical value. Okay? So let's look at something we know. Because I'm going to jump ahead and give you our formula. Our formula for our C% confidence interval looks like this. You have your statistic plus or minus your critical value, which we're going to call Z star, not Z hash, okay, times our standard error. Ooh. Sorry, that's a star. It's a really awful looking star. What is a star? It looks more like one of those characters from Astro. What is it? So the question is where does this number come from? It's a number we're going to use, right? So if we look at that number, imagine, let's look at what our critical value might be for 95%. So essentially, if we're going to do it for 95% confidence, we're saying that the true proportion is captured within this interval, right? And what is our area? Our area over here. What is this area? If we look at our Z table, right, that should correspond to Z value of negative 2 and a Z value of positive 2, right? So, if you get your handy-dandy Z table out, so we can do this with a calculator as well. We can do an inverse normal calculation for this, right? But if we're looking at 2 standard deviations below the mean, we're looking at this area right here, right? But that's not super precise, right? If we look at that value. So in order to get a better value, we are going to instead use a t-table. So we get a new table. It is in the back of your book, and I'll print them out for you guys. And it's this one. So from now on, rather than going to your Z table, if you want to find a level of confidence, let's see here if I can get a little better. We're going to go straight down to the bottom of this table here, and we'll get a value. So this is where we're going to get our critical value. So at 95%, this is our critical value Z star that we're going to use. Okay? So if we wanted 80%, our critical value that we'd use would be 1.282. These are better values because they take into account that it's a sample and they give you a little bit more of a, I call it a fudge factor. Your book calls it. All right, let's just go ahead and get into a problem. All right. So we're going to use, actually we're not going to use table A. We're going to use table B. Because it's better. It's the one you're going to want to use. Oh, the solution is on there. Yeah, I am asleep today. Let's pretend that never happened. I think that's a terrible example. Alright. Oh, awful. That's an awful example. Let's do this. I'm sorry. Here we go. That's better. Let's actually make a confidence interval, for goodness sake. Alright. Now the rubber has hit the road. Let's calculate and interpret a 99% confidence interval for P, the true proportion of pennies from the collection that are more than 10 years old. So, remember, P hat was 57 out of 102, which we said was approximately 0.559. Is that correct? Okay. We already checked conditions, right? I'm just going to say conditions. It's written down already there. All right, so let's go ahead and do this. So we want P hat plus or minus C star times the square root of P times 1 minus P hat, my bad, over N. Let's construct this thing. So that's going to be 0.559 plus or minus. Let's go ahead and get the Z star critical value from our D table, which is going to be far more correct. Again, this is in the back of your book, and I'll print one out for you and give it to you tomorrow. So, let's look at it. What was our confidence level? All right, 99%. So at 99%, I'm going to go over here to 99%, and this is going to be my critical value, 2.576. All right. So we got 2.576 times the square root of 0.559 times 1 minus 0.559, 0.441, thank you. All divided by our sample size of 102. Let's go ahead and calculate that. Let's get this. 2.576 times the square root. I better put this in parentheses. No, it's okay. More equals to 559 times this is, so that value is approximately 1.267 or 0.1267. Let's go 127. Yeah. Okay, so let's construct our interval then. Okay, so I need to add this value and subtract it. So I'm going to make an interval. Son of a gun. 0.559 minus 0.127 is going to be 0.432, and 0.559 plus 0.127 is 0.686. Okay. So now we constructed a confidence interval. It's time to interpret it. Okay, so we are 99% confident that the true proportion of pennies that are more than 10 years old in the collection is captured by the interval we get to do algebra problems like this. It is one of the few problems you actually have to. So suppose we wanted to estimate the true proportion of students at your school who have a tattoo with 95% confidence and a margin of error of no more than 0.10. How many students should be surveyed to estimate P with 95% within 0.10 with 95% confidence? Right. So what do we know? We need to know what n is, right? Yeah. Okay, so we have a formula. It gives us hat plus or minus z star times p hat 1 minus p hat over alright, we want our margin of error to be no more than 10. So in other words, we want this thing to be less than 10, right? So we can set up an equation that says that over here. Sorry, 0.10. We said wait. No more than. It's gotta be that. All right. So what is our critical value for C star? If it's at 95%, it's 1.96. times the square root of. So we're going to use a p-value of 0.5 because the margin of error is largest for a p-value of 0.5. And we can explore that a little bit more as we go. So we need to solve this equation. So we got 1. All right, so 0.5. All right, I got to get rid of this radical. So actually, first of all, I'm going to divide both sides by 1.96. So we get 0.51. If we round, that's what we'll find. Okay. And we have the square root of 0.25. And so we'll square both sides. So, okay. 0.003 around here in the south equals 2.25 over n. And we square both sides. Let's go ahead and solve this thing like a proportion. No, we just need to divide both sides by 0.03. We get 0.04. So that means that the sample size has to be greater than 96.